Yeah.
Cool, okay, I will fail.
We're going to walk through a couple examples based off of people asking questions in Tutoring Center. So we'll start off with, we're going to look at hydrogen NMR because that's where everybody's going to get kind of held up. I'm going to bet the vast majority of questions that we're going to talk about in here is going to be hydrogen NMR. Okay. So we've got a structure here. How many signals do I see in HNMR? How many signals do I see in the HNMR for this structure?
You can only see one.
All right. So two answers come out, 1 and 2. And for the people saying 2, it's because you're like, well, I see these 3 hydrogens all being the same, and I see these 3 hydrogens all being the same as each other. And you're right. Those hydrogens, as I've grouped them, are the same as each other. They're also the same as each other. I don't know how to describe that one. Okay. Due to an internal mirror plane, remember that from chirality, dealing with internal mirror planes? Here it comes back again. Okay. The hydrogens on both sides of that are identical to each other, which means I see a whopping 1 signal. Okay? Easy, right? Andrew, isn't that easy?
Well, yeah. How tall is the signal now? It's going to be 1 and 2.
Cool. If I have only 1 signal, how tall is it going to be? The tall has to do with relative to something else. If there's nothing else there, there's nothing to compare it to. So it is neither tall nor short. How many signals do I see?
2.
Okay. We're going to get 2 again, internal mirror plane, meaning the hydrogens on the outside are identical. Okay. And the ones sitting through the middle are identical to each other. So we're going to get 2 signals. Cool. What's the next thing we would introduce when we talk about HNMR? Okay. Officially, the word is integration that you're searching for, which is the area underneath the curve of the signal. Okay. I thought I was kind of an old school chemist, and then I talked to some old school chemists. The way they would figure out the integration ratio is they would literally print out the document, and they would get out scissors, and they would cut out the paper around the signal, and then they would weigh the pieces of paper and create a ratio based off of the mass of the paper in each of the signals. Like, that's just crazy to me. Okay, why? Because the mathematics hadn't caught up enough to actually be able to calculate the area underneath the curve for those very tiny peaks, so they would just cut out the paper. It was easier to do it that way. Okay, so we now can tell our computer to integrate for us, and it tells us a magic number. Okay. Other methods that can come out are looking at a plot of the integration where it shows a peak, kind of follow along, where there's no integration, there's no peak, so there's no area under the curve. Whoop, there's a peak, so now I have an area under the curve. Oh, and now I have no area under the curve again. And so what you would do is measure the height of each of those spikes, okay, to tell you the integration. Okay. You can do it sort of by inspection, which is what you're suggesting, just the raw height of the peak. The problem with the raw height of the peak is the area under the curve isn't dictated just based off the height of the peak. What else dictates the area underneath the curve? The width of the peak. And when we look at most of our spectra, the widths are about the same, so we can ballpark estimate height of peaks. Okay? ACS, for whatever reason, is living in the dark ages, and that's what they expect you to do. They don't give you integration information. I still don't understand that one. Okay, but that's how they've got it formatted. Okay, but back to our structure at hand. What's the integration? So you've told me there are two signals, so we'll say signal 1 and signal 2. That looks weird. I'm going to write signal 1 and 2. What should the integration be?
Should one be half as tall as the other?
Should one be half as tall as the other? So we're saying signal 1 is half the height of signal 2. Okay. And if we're using your height method, what you're saying then is if 1 is half the height of 2, your ratio is 1 to 2. Right?
Wouldn't it be that signal 2 is the 1 and then
Okay.
red
Okay.
is
Okay.
the half? Or-
2
Sorry, it's tall.
to 1. Okay, because we got color coding on it. Okay, I'll accept that. What do we think? Do we trust him? After all, he thinks this is easy.
It's boring.
It's boring. I'll give you that. What does integration give you information about? The number of hydrogens. How many red hydrogens are there? How many green hydrogens are there? What the instrument will tell you is a 3 to 1 ratio. So that 2 to 1 isn't taking into consideration the amount of hydrogens that are contributing to each of those signals. Okay? How is this information reported to you? Okay? The spectra or the instrument doesn't know what the structure of the compound is. All the instrument is doing to figure out your integration information is just saying, I see a hydrogen. Oh, I see another hydrogen. Does that hydrogen have the same chemical shift? If yes, it places the hydrogen in the same area under our curve or on our graph for chemical shift, making that peak taller. It's effectively a histogram. Kind of, sort of. So when our instrument looks at this, it just goes through and says, well, I see 6 red hydrogens and I see 2 green hydrogens. Okay, and it just counts them up. But that's looking at one molecule. How many molecules are we looking at? Okay, we're looking at a lot. So the number that's actually coming out, the computer's spitting out, it's not counting 6 and 2. We're probably counting 60,000 and 20,000 hydrogens. Do we want to look at 60,000 hydrogens and 20,000 hydrogens as an output for data? No, so what do we provide? The reduced ratio. Okay, so when we're talking about our integration, it typically reports the reduced ratio. Okay, so when we go through and look at this, if we're talking about the signal, this is saying that I see 4 hydrogens. Well, do I see 4 hydrogens in my structure? No, how many hydrogens are there? 8. I had to scale up the reduced ratio. So depending on the information given to you, you may be looking at a reduced ratio that doesn't tell you exactly how many hydrogens, it just tells you the ratio of hydrogens. Or you may get lucky and it tells you the exact amount of hydrogens. So you have to be really careful with looking at your, integration information to ensure what you're evaluating when you're talking about the hydrogens. Kind of makes sense?
So if you're only given one peak, it would have to be 1.
So if you only have one peak, there's nothing to compare it to. So your integration is 1. Okay? How many signals do we see in our hydrogen NMR?
Should just be 1.
Okay? You don't have to answer this out loud, but are you looking at it being like, I don't see any hydrogens, so I must see nothing? Okay? Because I guarantee you, if we asked that question 2 or 3 weeks ago, we would have said 0 hydrogens. So you've picked up some content. So when you're looking at this, you recognize that those are carbons, and to satisfy the octet, I need hydrogens coming off of each of those. So we should see a signal in our HNMR. Now the question becomes, how many signals should we see? Should I see 6? Okay. Due to this mirror plane, those two hydrogens are identical to each other. Due to that mirror plane, these two hydrogens are identical to each other. Due to that mirror plane, those hydrogens are identical to each other, which means one signal. Okay? All of those stack out as equivalent. And if you're like, but you didn't circle everything exactly the same, you have to remember as we circled, we just added one more color in that system. But the blue ones were still the same as each other, okay, which meant when I circled green, the blue were also in there. When I circled the orange, okay, I have to recognize that the green and the blue were also in there because they're equivalent to each other. Which means every single one of those hydrogens is exactly chemically identical. They are indistinguishable from every other hydrogen. That generates one signal. Kind of, sort of? Let's just erase everything and draw it again. Now how many hydrogen signals? So we're hearing 2. Okay, let's walk through that. And thanks, Andrew. It makes me feel better when you nod your head and say agreement with this. Okay. There's a hydrogen, right? Is that an internal mirror plane? Maybe not as drawn, but if I rotate that sigma bond just a little bit, I can rotate it so that I can split one of those hydrogen atoms perfectly in half, and then I would reflect wedge and dash across the backside. Meaning, that is indeed a mirror plane. That is indeed a mirror plane that you theoretically expressed and learned about when we talked about chirality. Yay! Which means the hydrogen over here is identical to it. Okay. Those people saying 2, how about this hydrogen? Is that identical to the blue one? No, why not? Is there a mirror plane that runs through there? Do you see this CH3 reflect down, come on, pen, down to here? So what does that mean? Is that a mirror plane? Nope. Which means that green hydrogen is different from the blue hydrogen. How about over here? Same as the other green one. How about this hydrogen? Is that the same as the green one or the blue one? Nope, that one's different. Got a problem here, guys. You told me there were 2, and I'm already at 3, and I still have 3 hydrogens left. That one's clearly different from the other ones, right? How about from this one? Chemically identical. Why? Sigma bond rotations will allow us to rotate that carbon bond, the carbon-phenyl ring bond, so that those hydrogens occupy the exact same space relative to each other. which means also chemically identical. So this particular structure has how many unique hydrogens? 4 unique hydrogens. So I would get 4 signals. What would the integration be for this? One to 2 to 2 to 3. Your ratio is the count of hydrogens, because I can't reduce this ratio any further because of that 1. Kind of, sort of?
Can you go over like why the rings are all different?
Wait, sorry. You asked a different question that I was about to answer. Try again.
Can you explain why again, like the hydrogens in the ring are all different?
Okay. Are you okay with the blue hydrogens being the same as each other, the green hydrogens being the same, and the red?
Yes.
Okay. So cool. What does the blue hydrogen see when it looks to the left or right, whichever direction that is? We'll call that S because it's going counterclockwise. What does it see? This is at you. What's it see up there? Cool. Sees the carbon. When it looks to the right, what does it see? It sees the hydrogen. What does our green hydrogen see when it looks to the left?
Nothing on the other side.
When it looks to that left, what does it see? A hydrogen. When the other one looks the other way, what does it see? A hydrogen. Is the green one different from the blue? They see different environments. Does that make sense? Okay. And I just saw your head cock, so maybe you're potentially projecting where we're going to go next. So let's get rid of the blue one. This one we said to the S, it's seeing hydrogen. This one we said to the R, we were seeing hydrogen. What does the red one see when it looks to the left? Hydrogen. What does it see when it looks to the other side? Hydrogen. So how is the green different from the red? They see the same things left and right. Shouldn't they be the same? What does it see when it looks directly across? It sees a carbon. What does the green one see when it looks directly across? Can I tell a difference between them? Yep. That's why they're all different from each other. Okay? So the chemically distinct becomes really challenging because what you're trying to do, the way that I have always envisioned it, is that if I built the model and I pointed to a hydrogen and then I gave the model to somebody else, said, do whatever you want with the model, don't break any bonds, but do whatever you want with the model, can I point to the exact same hydrogen? If I can point to the exact same one every single time, that is 100% unique from everything else. If I'm confusing it with another hydrogen, then it has something that's chemically identical to it, and they would count as their own signal. Kind of, sort of? That requires using the models again. Almost like there's a reason I said it was required to purchase for the class. Kind of okay? If you're not okay with this, you should speak up because it's only going to get worse. You sure? Okay. How many unique hydrogens? Talk to people around you, see what they think. What do you guys think? Words?
Sorry.
No.
These are all different. So if this is
Okay, you see 3? Okay.
Is it because like these two are the same, so it's 1 and then 2?
So let's slowly piece it together. So one thing that I would argue, let's put it this way. Okay, I can't see what you've got written if you wrote anything, but you two in front did something different written than what she wrote. What did you two in front do? Ooh, you drew in the hydrogens. Does that change our interpretation? Is that going to change your answer if you see all the hydrogens? Dang it. Okay, so what does that mean? You need to draw your hydrogens. Okay. Because you've kind of reflexed, or you maybe have gotten good enough where you don't feel you have to draw the hydrogens, it's now coming back to bite you because you have to know about the implied ones to be able to answer the question. Okay. Then let's break down what you went through and said. Okay. So with those hydrogens, you were saying those were all the same. Okay. And you were saying they were the same as these. Yeah? Okay. Why?
They're the same formula?
They're both CH3s. Cool. This CH3 looks this way. What does it see? Okay. This one looks this way. What does it see? Are those carbons identical?
No, because one's attached to the other.
If they're not identical,
Oh, then they're different. Yeah.
So I think it's either the rest 4 or 5.
I would say 3. Because if I was to take this normal
okay, wait, you don't know about what?
tank, it would be 2. But now that I'm adding another
Explain why this one is different from this one.
it's forcing
Okay.
the middle 2.
So you're saying they're different. You're not saying they're different. You labeled them both as one, right?
Yeah.
So, fight.
Would this plane of symmetry be here? So this carbon only has 2 on this side, or down here.
So, and this is where we get locked up. I'll try and build a model for this so we can see it a little bit better. Oh, I should not have been recording because we're looking at a model kit. So what I've done is built the model for this structure. So does everybody see this structure matching with what's up there? Or is it this way? Other way? Okay. Everybody see it matching the drawing up there? Okay, cool. So now what we want to do is try and think through the differences between all of these hydrogens. Okay, and I guess I'll do some drawing. So we've got a red hydrogen that I drew on here. Where's that red hydrogen in this? Probably a bad idea to ask that question, but I'm asking anyway. Am I holding on to it? No. No, okay. Where's the red hydrogen?
To your left.
Should be all the way out there, right? So we got that red hydrogen. Okay? So that position had 3 hydrogens, or really has 3 hydrogens. Are any of them different from each other? Why not? What's that? So we'll come back to that source question in a different statement. But source is going to be problematic. Okay? And we'll talk about why in a little bit. Screw it. No, we'll just do it right now. Are those hydrogens on the same source? Yes. Identical or different? Yeah. I appreciate the gesture. All right. This is fun, because as we asked that, what happened? Wow, that's why. If you listened real carefully, I heard someone say identical, and I heard someone else say different. Huh. Fascinating. Okay, so I feel kind of bad. Someone actually built this. Usually it's just me messing around. Okay, so there's our structure, right? Am I holding it at the right angle for what's drawn? I'm holding it? We got it? Okay, and what I'm asking about is those 2 hydrogens. Are they identical to each other? Okay, so if we use the wording you used for the previous one with the red hydrogens on the sp3 one, you said same source. Are these hydrogens connected to the same source? Yes. Are they identical? No, why not? This top one sees that methyl. What does the bottom one see? A hydrogen. Okay? So when we went back over here, well, doesn't this hydrogen, see this big old chunky thing up here, and then this hydrogen doesn't? Wouldn't that make them different? This is a sigma bond, and that sigma bond can freely rotate, which allows each of those individual hydrogens at that position to experience the exact same chemical environment. Why is this one different? Double bond meant can't rotate. That hydrogen is locked into that space, and it can't exhibit that exact same chemical environment. So I understand what you're trying to say with source. It's dangerous, particularly when you bring in double bonds. Does that make sense? Okay. So how else could we look at it? Well, one, we could use the model kit, and we could use the model kit and recognize that, oh, they're all occupying the same thing, which is ultimately actually saying that there's an internal mirror plane running through that carbon. There's one here that makes these hydrogens identical to each other. There's one there. There's one there. So that sigma bond rotation allows all of those hydrogens to be 100% chemically identical. Make sense? Yeah? I promise it gets worse. Okay. So what happened? Not yet, though. Hopefully now it's still nice. Okay. As we continue through our structure, is that really the structure? Yeah, I guess it is. Yeah, I guess it is. What's happening at that green carbon? I also have two hydrogens, right? So here's my two hydrogens. Do they see the same chemical environment? Right? And if we can tweak it like this, okay? This one sees a methyl, that one sees a methyl. But if I rotate, ooh, this one sees a hydrogen, this one sees a methyl. Newman projections? So does that make those hydrogens different? No, why not? Continue to rotate, hydrogen aligns. Everybody get it? Which means those two hydrogens, same chemical environment. Right, so the green hydrogens are nailed down. How about this one? Is that one different from everything else?
Yes.
Why is that one different from everything else?
Because it's, whenever something else is rotating, it's on the rotation. So every time it's,
Okay, you're making it harder than I think it needs to be.
okay, it's just a
It's okay. Yeah. Okay. The green ones, there were two hydrogens connected through. They were at the exact same source. Again, source is dangerous. But if we look at the orange one, there's only one hydrogen there. So it must be different from the green ones because the green ones have two hydrogens. It must be different from the red ones because the red one has three hydrogens. Yeah? What about these three hydrogens? Should those be their own color or should they actually be red? Okay, so if we're looking at our structure, I believe, yeah? We're looking at the model, right? Yeah? Okay, my left hand, blue, my right hand, red. Should those be the same or are they different? Okay, what does my left hand see? It goes up to a carbon that's connected to a CH3. What does my right hand go to? It goes to a carbon that's connected to not a CH3, which means they're different. Okay? So the blue one needs to be unique from the red one. Colors. How about these ones? Those purple ones. Should they be purple or should they be red?
purple.
They should be purple, not red. Should they be blue? Okay. And that can be a hard one because we're looking at it. Well, this one looks down and it sees that guy. You mean it sees that guy? Everybody see that? Should I do that again? There was our original structure. This methyl, our purple methyl, sees that red hydrogen, right? Okay. Whereas the blue one doesn't see it. Like, that's really far away. Can't possibly be the same, except what did I do? Does it see it now? Yeah. What did I do to allow it to see it? A sigma bond rotation. That sigma bond rotation brings the purple and the blue into the exact same environment. That's using the model, and that can be really hard to see. But because that's true, there's technically an internal mirror plane within this that allows us to do that. Okay? So erase those. Those shouldn't be purple. Those need to be blue. Okay? Where's the internal mirror plane? It's right through there. Does that look like an internal mirror plane to you? And for the people saying yes, keep your mouth shut. Right? If that's an internal mirror plane, what should I see right here? I should see red hydrogens. But I don't. Okay? That is the internal mirror plane drawn very, very crudely. Where's our internal mirror plane? Okay, so there's our structure, right? Okay, the internal mirror plane I'm saying is to go right through here. That doesn't look like an internal mirror plane, right? Because if I put through, this methyl group doesn't reflect across. Do you see the internal mirror plane now? Oh, son of a, I can't get my hand out of the way. That's the best I can do. The internal mirror plane is going to split that molecule perfectly in half, making these two methyl groups identical to each other. To get to that point, I had to do a sigma bond rotation to bring it into alignment. When we talked about superimposability, were those superimposable? Yeah, they were. But if I try to bring those two structures on top of each other, do they superimpose? No. What did I have to do? I had to realize that I could do a sigma bond rotation, that at one of their rotational states, they superimposed. I'm doing the exact same system here. In one of my rotational states, I can see the internal mirror plane. I'll speak louder so people outside don't infect us. Sorry. Simple pleasures. Does that make sense? Okay. Well, yeah. You got to be good with this. We good? Okay. I'll screw off, just erase everything. We had what? Red hydrogen, we had green hydrogens, and we had our blue hydrogen out here. Except now what I'm going to do is I want to make this a chlorine. Why? How is this going to change anything? Say that again? Okay, so one option, say, oh, well, you didn't specify the hydrogens, the rest of the hydrogens on the blue and the rest of the hydrogens on the red. Why did I not specify them? Those other hydrogens were identical, so I don't really care. Okay? You might also say, well, you're missing the hydrogen on that middle one, that orange one. You're right, I am missing that one. That's a fair play. I should have drawn that one. That's actually my bad. Okay? What else is more complex about this problem?
We're talking about H, M, and R, right? Or so.
We don't even have to bring in spectroscopy. This is unit 1. Why is this more problematic to worry about? Someone said it.
It's chiral.
It's chiral. I have a carbon that is connected to 4 distinguishable groups. which means if I'm going to look at this molecule, I need to be a little bit more careful with my assessment of it. Let's go through and call this chlorine wedged and this hydrogen dashed. Is this going to change anything about this system? What do you guys think? Does it change anything? Okay, some people are like, you're saying it like it does, so I'm going to trust that it does. Yeah, that's a good idea. It's a good trust. Sometimes it's good trust. Sometimes I just say it to be a jerk. I'm going to introduce a brown atom. And this brown atom is going to represent what? Awesome. That's representing our hydrogen. Okay? That hydrogen, the brown atom that I'm calling hydrogen, is one of our green... Oh, my God. This... I can color code. We'll do it this way, right? I can get... Do I have brown? I have brown. Look at that. Brown, hydrogen. Green. I don't want green. What do I want in front? Pink. Let's go with pink. Color code. You're really good at catching those. Sorry, just checking.
I catch it on bounce.
I'm going to change that last hydrogen to a black hydrogen. Okay, I'm just running out of colors. So if we look at our structure, right? Okay, there's our carbon backbone. Everybody got it? Carbon backbone? We got the green, chlorine, coming at you. Everybody okay with that? Okay. Should we show wedges and dashes for our red and our brown hydrogens? Okay, let's show wedges and dashes. Which one's wedged? Okay. The red one is wedged. What's the brown one? We good with all that? Okay. Why is this going to become important? Well, when we first looked at it, what did we say was the difference between the red and the brown?
They could both see the methyl.
They both saw everything exactly the same, right? So there was no difference between them. Right? Okay. So what we're concerned about is that red and that brown, okay? And in particular, what changed? What was the big change we made? Why is this molecule crazy and different and weird? Not just chlorine. The chirality. The chirality becomes important. So what I'm going to do is now shift my focus and look at a Newman projection. Yay, Newman projections. Right? So there's a Newman projection. We'll put the chlorine aiming at you in front. Okay, if I look at where the red atom is, okay, it's gauche to the green. Everybody see that? Okay, it's also gauche to not a hydrogen. It's anti to a hydrogen. It's gauche to the methyl, that carbon down there. Okay? If you're wondering why this is important, well, let's go ahead and let's rotate this guy around. Is this occupying the same space? You might say, well, it's gauche and gauche, right? But is it occupying the same relative space for everything else? Is this the same energy structure as the one I had over here? Here, if I look, my carbons are on opposite sides, which means anti. If I move to here, where are my carbons? Gauche, which means is this brown atom experiencing the exact same environment as the red atom? No. And if they're experiencing a different environment, what does that mean? They are chemically different. What does that mean?
Yeah, two different hydrogens.
I now have two different hydrogens at that position. Why has this become important? How many signals do I see?
5.
I have my black hydrogen. I have my brown hydrogen. I have my red hydrogen. I have my blue hydrogen. And I have, running out of colors. my orange hydrogen. Why does this become important to me? Okay, well, now what we want to do is layer in the next piece of information. The next piece of information that we've been layering in was looking at what? The integration. How many hydrogens are represented by the black hydrogen? Not one. Remember, we had those implied. We had a 3. How many hydrogens are represented by the brown hydrogen? 1. How many hydrogens represented by the red hydrogen? How many hydrogens represented by the blue?
3.
How many hydrogens represented by the orange?
1.
1. So a structure that went from 4 unique hydrogens now blew up to 5 unique hydrogens. Okay? And within that system, I don't remember the color coding, but before we had what? 3, 2, 1, and then the last hydrogen, because we had 2 methyl groups, came out at 6. Kind of, sort of, vaguely remember in that structure. Blue hydrogen, orange hydrogen, green hydrogen, red hydrogen. Everybody got it? So what had 4 signals, now, because I've added chirality, same backbone, I get 5 signals. Insult to injury. Remember you said source, right? Take a look at the red hydrogen and the brown hydrogen. Are they the same source?
Yes.
Yeah. And yet they are chemically different. But I can do bond rotations. Why are they still chemically different?
So the wedges and dashes of the chlorine.
Because of the chiral atom right next door. That's what shafts my approach. Okay? Why does this become important? Well, if you have a chiral atom in your molecule and we run spectra on it, how is it going to manifest? It's going to manifest like a shit show. Okay? And you're going to see tons of extra signals appear. And those tons of extra signals are likely going to come out to integrations of 1. Okay? And for people wondering, why are we talking about this? Well, we're talking about it because it's important. Understanding where these things are coming from and how they manifest is exactly what spectroscopy is talking about. Okay? But for those not in the clue, there was a group of students working on the spectroscopy packet in the tutoring center. And in particular, question number 4. Question number 4 is a brutally challenging question to deal with. And what those students struggled to deal with is they kept hitting this system where they were getting bizarre integration information. Guess what the bizarre integration information was? A whole bunch of 1 hydrogen signals. Why? Because there's a chiral atom present, and that chiral atom shafts your whole approach. It makes your integration system look horrible. And integration isn't the last step, right? It also is going to introduce a whole nother level of crap when it comes to multiplicity. Should we open that can now? Yes, okay. All I needed was a yes from somebody that wasn't working on the assignment. Okay, so what we're going to do, let's see, what do we want to do? Should we double back to the simpler version to look at our multiplicity? Yeah? Okay, let's do that. So clear everything away. Red hydrogen, green hydrogen, blue hydrogen, orange hydrogen. So we get 4 signals. We're representing those 4 signals by those 4 colors. If we look at our integration information, our blue hydrogen had how many hydrogens? 6, because remember this one was identical to it, or the person that said 3. And green hydrogen had how many hydrogens? 2. I don't know why I did the orange hydrogen for you. Red hydrogen had how many? 3. That's all our integration information. But now what we want to piece together is what's going to happen with our splitting pattern. What would our multiplicity look like? So our multiplicity has to do with the number of neighbors. So before we start saying multiplicity, let's look at neighbors. When I look at this red hydrogen, I want to figure out how many neighbors it has. Well, what makes a neighbor?
Bond, 3 bond.
It must be 3 bonds or within 3 bonds away. That within is going to be a real biter, so we got to pay attention to that one. Within 3 bonds. Okay, so we could start counting it out. I could go 1 bond from the hydrogen. I'm going to start at the red one. I'll go 1 bond, 2 bonds. I'm out of hydrogen. Does that hydrogen count as a neighbor? No, why not? Same house. Okay, not necessarily the same source, but it's a similar concept. It's the same chemical identity, so that doesn't count as a neighbor.
So it's kind of like what you were saying in the video was like the roommate.
Yes, exactly that. Okay, so there's 2 bonds, there's 3 bonds. What am I at? I'm at a hydrogen. So that green hydrogen is a neighbor to the red hydrogen. How do I want to do this? Red hydrogen, does that make sense? HN for neighbors? Yeah, I didn't like it either. How about we just say neighbors and we'll just make a run? We'll make it in black so it's not color coded. So if we're looking at the red hydrogen, how many neighbors does it have? Well, it has that green hydrogen as a neighbor. So that counts as, we just hit a dilemma. Does that count as 1 or 2? Well, the hydrogen I pointed to counts as 1 because it's 1 hydrogen. But what do I have to remember? There were 2 people living in that house. Both of them count as neighbors. So it has 2 neighbors. I need to put the N on it. Reflex. Does that make sense? Okay. Let's move to the blue hydrogen. We'll see why we skipped the other ones in a second. Okay. If we move to the blue hydrogen, I only have to do it for one of my hydrogens. There's 1 bond. There's 2 bonds. There's 3 bonds. What am I at? A hydrogen. Okay, so there's 1 neighbor. What if I did 1, 2, 3 bonds? What am I at? Carbon, that doesn't count. Okay, if I went a 4th bond, then I would be at hydrogen. But that's not equal to or less than 3. So that doesn't count as a neighbor. Which means how many neighbors do I have for the blue hydrogens? I have 1. Sorry, I talked over you. What'd you say?
Is that where you add the +1?
That's the multiplicity. I don't even want to deal with that quite yet.
All right.
But yeah, that's the next layer. Green hydrogen or orange hydrogen?
Orange.
Fine.
Green.
I shouldn't have asked if I was going to. Okay. How many neighbors do we have for the orange hydrogen? Okay. How'd you get 6? Walk me through it. 1, 2, 3, right? That's a hydrogen. That's only 1. How'd you get 6? Did you say 6?
I didn't say 6.
Oh, who said 6? You said 6. Why'd you say 6? Remember, that top one had 3 hydrogens with it. I also have 3 chemically identical down here, which means even though they're in a different source, still chemically identical, that's 6 neighbors. But, of course there's a but. Where the hell? And I'll color code that one actually. Why but?
Just the 3rd row.
2, 3 to the.
I could have gone 1, 2, 3. Which means the green ones are also neighbors. So I get 6 hydrogens and 2 hydrogens. What does that mean for me? If I'm lucky, it means I have 8 hydrogen neighbors. We'll talk about lucky in a second. What happens with my green hydrogens? How many neighbors do they have? Slowly. I would go 1, 2, 3. There's 1 hydrogen from my orange, and 1, 2, 3, I also have the red, has 3 hydrogen, which means the total signal that I would get would be, again, if I'm lucky, a 4 hydrogen signal. Okay? How does this then manifest into the number of peaks? Because that's now what we see within the spectra. Okay? N plus 1 is your number of peaks. So starting with the red hydrogens, if I have 2 neighbors, that's going to turn into 3 peaks. 1, 2, 3. Theoretically matching the pattern of 1 height, the middle peak will be twice the height, and then another one matching 1 height. Okay? What happens with the blue ones? Well, they only have 1 neighbor, so 1 neighbor plus 1 is 2 peaks. The intensity, they're the same height. Okay? That's the peak patterning that comes out of it. What happens when I hit 8 hydrogens for our orange neighbor? Why did I... This is going to be 9 peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Again, notice the peak patterning. We go up and we must come down, and we come down in a symmetrical system. What happens with the green hydrogen?
5 peaks.
5 peaks. 1, 2, 3, 4, 5. So far, so good? Okay. What we just drew at the bottom, admittedly kind of smaller than I wanted to do, but for an important reason we'll see here in a second, is the simple version of it. Okay, what are we talking about, simple version? Well, the red hydrogen and the blue hydrogen, those are just going to be fine. We don't have to worry about those. There's nothing fancy with those. The orange and the green potentially can turn into a mess. Okay, why can they turn into a mess? What we're doing when we're talking about multiplicity is your parent hydrogen, so let's talk about the orange one. That orange hydrogen sees other hydrogens. That causes its signal to break apart. And what we're seeing is all the possible ways that it could break apart. So there's a very low probability of it breaking apart in this particular fashion. There's a higher probability for the taller peak. Okay, so it's how those magnets all interact with each other. And in that particular scenario, there's 8 flipping magnets talking to each other. So we're getting a whole bunch of different combinations of north to south ends of your magnets, effectively. That's what's generating that distribution. Kind of, sort of? Okay. There's some people that didn't seem to agree with that. All I can really do is a really, really brutally simple example. Let's just look at the example where I have 1 neighbor. So a hydrogen atom is a magnet. Positive and negative end, north and south end. If I have a neighbor, that neighbor can come in and align either positive, negative, or it could come in and align negative, positive. Is that going to change my output? Yeah. In one case, we're getting effectively a repulsion of our magnets. In the other case, we're getting an attraction. So when I have 1 neighbor, how many peaks do I get? 2. Why? An attraction interaction and a repulsion interaction. That's what's happening. Add in another neighbor. Now, how do all of those potential magnets stack and interact with each other? And if you look at all the possible interactions, guess what you're going to find? You're going to find there's 3 types of interactions. Okay? You'll get one of those types of interactions twice as populous as the other 2. And that's why we're getting that peak patterning that comes out of it. Okay? So if you're really good with probabilities in mathematics, you can play around with that and figure that all out to show all of that, and that would be lovely and awesome, and I greatly appreciate it. Sort of. Okay? How can this become more problematic? Well, in the case of the orange one, I have a blue hydrogen and a green hydrogen. Those are different neighbors. Is it going to interact the same with those neighbors? No. Right? So for instance, where I live, right, we're in the middle. I've got neighbors on either side, never mind people across the street, but either side of us. One of those neighbors, I know their names and we talk a lot and we figure out where they're going. They're going off to San Diego this weekend. That's lovely. The other guy, his name might be Ron. We'll never check, right? Right? And the only conversations I've had with him have been mostly grunts as he runs home, because he goes running. That's it. I know nothing about him. So how those neighbors affect me, way different. One, there's a stronger attraction with, so I'm going to get a different splitting pattern. The other one has a weaker attraction, I'm going to get a different splitting pattern. How does that manifest? Okay, well, for the 6 hydrogens, really, Mike? Jerk. Let's say it interacts with the 6 hydrogen signal strongest. How many peaks would I get? 7. 1, 2, 3, 4, 5, 6, 7. Did I do that right? Ish? Okay, cool. So the signal splits into 7 peaks. But I must also be split by my other neighbor. That one's a weaker interaction. Okay? Which means the split of the signal is smaller. I don't get as big of a spread in the signals. Okay? And because I interacted with the blue one strongest, that's exciting. That's already split. So now my signal isn't starting with just one line, it's starting with 7 lines. Which means when I go through to look at that 2H, how many peaks should I get? 3. I will get 3 for this first little tiny one. And I'll get 3 for that next taller one. And I'll get 3 for that next taller one. And I'll get 3 for the next taller one. And I'll get 3 for that one. And that is my splitting pattern. And if you're like, oh my God, that's incredibly complex, it is. But we had 1, 2, 3, 4, did I count it right? 5, yeah I did, 6, 7. We have 7 sets of 3 peaks. Also known as splitting of splitting. That can happen? Yes. Okay. How often does it happen? Well, here's the added thing to realize. To get the signals to split requires a strong magnet. The magnet is what's causing those signals to split away from each other. If you have a weak magnet, you don't get the signal, you don't get the resolution of the signal splitting away from each other. And because you don't get that resolution, what does it start to turn into? This giant, I'm far enough, clusterfuck of a splitting pattern turns into 9 peaks. Why? Because each of those signals overlaps each other. They overlap in each other in a way that those signals get additive, and some of them get taller, some of them don't get shorter, but they stay the same height. And the net result is we see that 8 hydrogen split at the bottom, or 9 peaks. Okay? If we lean into this even further, do we expect to even see 9 peaks? This is corresponding to a single hydrogen, which means how tall is that single hydrogen peak? It's going to be pretty short, because I've got other signals coming in at, 6 hydrogens. but I have to split that single hydrogen peak into 9 other peaks, which means that single hydrogen that may have been kind of short is going to do what? And it's going to shrink because now the width of my signal jumps up. You said you wanted to talk about it. Yay?
So it's smaller because of the window, so it's like a
Area underneath the curve is the height and the width.
yeah.
So when you're measuring the height, it's not the height of just any one of that set, it's the total set.
Okay.
And so if we're only looking at a 1 hydrogen signal, that's already going to be lower intensity that I'm now splitting across 9 peaks. That's going to be almost in the baseline. That becomes really hard to pick up.
So, like, would you even be able to visually see that at all?
So that now starts to shift us away from what should the NMR show us, what does it have the capability to potentially do versus what it actually shows us. Okay? That's a subtle differentiation that ultimately boils down to the simplest approaches that we went through at the bottom.
So we would have to go through this process just to say that it exists?
So it depends on the question.
Okay.
Right? So if the question is, tell me what the structure is,
Then I would have to go through new multiplicity. No?
not necessarily. Right? When would you have to deal with this nasty multiplicity? When you're looking at a system that you have a hydrogen that has different neighbors. If you're looking at a hydrogen that does not have different neighbors, do you worry about it? No. If you look at a spectra and you're looking at your answer and you're like, oh, this answer shows that I have different neighbors, do you need to worry about it? Does your spectra say you have to worry about it? Probably not. So don't worry about it. Okay? Where you're encountering this nasty splitting process really boils down to very small select cases. You're following the same patterning that we go through to get the bottom case, but it extrapolates and becomes a much larger issue in other scenarios. So we have to be aware of it in case it shows up. Question 4. Kind of, sort of?
So the splitting happens at 7 because of the 6 hydrogen neighbors that are the same. So
Yep.
splitting occurs there, but there's 2
won't
hydrogen neighbors.
Also occur there.
So it would have a splitting of 7 with little tiny.
Each of those 7 peaks turns into their own
Those are the
3 peaks.
Okay, so it's still at the bottom near the whatever x-axis.
Yeah.
There would be.
There would be a giant flush of peaks. Okay. With this particular structure, I doubt any of the magnets that we've got access to would show the resolution on that. Okay? Because to get that resolution, you need a really strong magnet. Okay? What's the size of the magnet we've got? 90 megahertz. Well, that sounds like a big number. ASU's baseline, so when you go to publish something, if you're going to publish something with NMR results, the baseline you must obtain is 400 megahertz. Okay? We're not even a fourth of that level of quality. Our instrument can't pick up that for jack. Okay? What is it going to show? It's not even going to show this. What it's going to show is one broad peak because it can't resolve each of those individual lines. So that resolution comes from the strength of the magnet. The strength of the magnet allows you to resolve and see those things, but the chemical shift stays constant, regardless of the magnet size. Kind of, sort of? For this signal, as we discussed it, this would be a septet, because there's 7 sets of peaks, a septet of triplets. What happens for our green signal? If we do the complex splitting pattern for our green signal, how many neighbors does it see? One neighbor, which means a doublet. A doublet of, how many neighbors does it see? 3, which means 4 peaks, which means this is a doublet of quartets. Okay. What does that assume? That assumes the orange split the green first. It could also be a quartet of doublets. How do you know which one it's going to be? You don't. You run the spectra and you see. How do you see it on a multiple choice? Both of those are valid answers. Only one of them would show up as an answer. Kind of, sort of? This wasn't even supposed to be brain breaking yet. I would argue the splitting pattern gets cleaner in the next set. Are we ready for the next one? Optimism, Serenity, optimism. Maybe you shouldn't have been optimistic. Sorry. I just started to kind of process through all the pieces in this.
It's okay, I wasn't.
I would say that hurts my feelings, but it doesn't. I fully understand and appreciate the pain. Okay. Do we need to go through the integration? Are we okay with the integration? This is where you should respond. Are you okay with the integration? Yes. Okay. Let's look at the hellish splitting patterns. Okay. And by hellish, let's start where it's not hellish. Where we're going to start is with the blue. Okay. For that blue hydrogen, how many neighbors does it have? This one's the easier one. It has one neighbor. It only sees the orange hydrogen as a neighbor. So that, has one neighbor. So how many peaks would that be? 2 peaks. We get 2 peaks of equal intensity. Okay. Now things start to fall apart. Let's take a look at the orange hydrogen. How many neighbors does it have? And if you're saying 8, you forgot that this is chlorine. It should have 5 neighbors. Okay, it has 3 neighbors from the blue. It has 1 neighbor from the green, and unfortunately, it has 1 neighbor from the brown. In a lovely, happy world, what does that turn into? That would be 5 neighbors. That gives us 6 peaks. Okay, I'm not going to draw that one. What we'll draw, we'll draw the other one. Okay, and this is where it becomes nasty. For the brown hydrogen, how many peaks do we have? 2. So we get 2 peaks. For the green hydrogen, what happens? Also splits into 2 peaks. But my signal has already split into 2 peaks, which means I need a little bit more space there. And now I see the blue neighbors, which is 4 peaks. So now each of those needs to split into 4 peaks, which I'm not doing a very good job of drawing it to scale, and I keep drawing eyes.
Can you back up a little bit? I'm confused when you went to the board, when you started adding in the blue. So I see that you did the one.
The green signal splits our 2 peaks into 2 peaks. So each of those brown signals now must split into 2 peaks. Which is why at this point, how many peaks do we have? we have 4 peaks, which is a good place to go. Okay? You can use all derivations of that. Okay? Now we move to the blue signal. 3 neighbors. If I have 3 neighbors, how many peaks? I need 4. I need 4 for each and every single one of the signals I have. Which means that first brown line needs to turn into 4 peaks. The second green line needs to turn into 4 peaks. The third second brown line needs to turn into 4 peaks. Okay? The last green line needs to turn into 4 peaks. Each signal gets split. This is why you hope and pray and cross your fingers that the instrument isn't strong enough to detect it, and what do we see instead? 6 peaks. What would this splitting pattern be? A doublet of quartets. Yay. Okay. That one is getting so refined that more than likely that's not going to be picked up by the instrument, and what we would see instead is just 6 peaks. What happens with the green hydrogen?
It's just seeing one neighbor of the brown.
It sees the brown hydrogen, yeah. Oh, God. This just got really gross. It's been gross for a while.
Does it see the orange one as well?
Is the orange one within 3 bonds?
That's it? Oh,
What'd you just say?
no, it doesn't.
Stop.
It's just.
It's the same thing.
So we get to do it again. Okay, that would be 6 peaks. And what's that going to look like? It's going to look like the thing that we drew over there, more or less. What happens with the brown hydrogen?
It's the same thing.
The same thing. What happens with the red hydrogen? The red hydrogen is actually a nice one when it comes to splitting. It sees the green hydrogen and it sees the brown hydrogen. That's it. What does our signal split into if we see a green hydrogen? 2 peaks. If I now see the brown hydrogen, and so that red one gets called a doublet of doublets, because it's 2 sets of 2 peaks. You opened the can, not me.
To be fair though, aren't we gonna have to do this like in a couple minutes?
So, and then that becomes the next thing, is everybody looks at us and goes, oh my God, I'm going to have to do this every single time. Fuck no, come on. Okay? You're doing this in very select circumstances. Okay? You're getting put examples that don't explode like this. Because when it explodes like this, it becomes a pain to differentiate and control. Okay? So the examples that you'll see on your exam, you'll get 1, maybe 2 multiple choice questions asking about splitting of splitting. That's it. Are you responsible for normal splitting? Yeah, you'll get lots of those questions if you understand splitting of lots. If you understand splitting of splitting, guess what you probably also understand? Normal splitting. Okay? Even then, you're like, splitting is too hard, I don't want to do it. Okay, don't do it. It's still going to be on the exam, you just won't get those points. That's also okay. That's not going to be the end of the world as far as your processing of spectra goes. Okay? Because you don't have to get all the way into the splitting patterns to be able to analyze what an actual structure is. Okay? You can get that information by looking at the IR, the mass spec, the carbon NMR, the HNMR, and then if you're really, really unlucky, where else can you look? Multiple choice. Remember, you do also have multiple choice. And so when we're considering all of this content, where you guys are zeroing in with questions is on the hardest stuff. And that's absolutely fair. I get that. You will see questions about the hardest stuff. Don't forget, you got a lot of easier stuff that you've also got to be able to evaluate. Focus on that, particularly if this is stumping you. Kind of, sort of? Officially, you get one signal with no color coding behind it, so that one I wanted to actually turn it into that final thing. But really, the way I've done it in the past is I would say green, I get a signal, green, I get a signal. And then the brown as a doublet splits that signal into a doublet and a doublet. Does that kind of make sense? Okay. Last thing that I'll mention before we're officially done. The spectroscopy packet, particularly if you're not in lab, you should still go through and do. Right? Even if you're in lab, you should still go through and do. Right? Why? It provides lots of practice behind each of these techniques. So if you can put together the spectroscopy packet, right, ignoring the hard ones or even doing bits and pieces of those, you're in a really good place for the exam. Right? Because that spectroscopy packet has you analyze all 4 things to get to a final answer. The exam isn't just here's 4 of these, do it. Okay? The exam is going to ask nitpicking details about each of these. When you look at this IR, what functional group do you see? Right? When you look at this particular range, what things show up? Right? Look at your smart work homework. Your smart work homework provides some context of things that can be asked in multiple choice type fashions. So don't freak out and be like, well, I can't get to a structure. You don't have to get to a structure all the time. What you need to be able to do is process some of those individual pieces. Should you still go through and work through the packet? 100%. What's the incentive to make you do that? Within the show your work portion of the exam, I will pick one of these questions. Verbatim. Copy and paste, here it is. You tell me all the work. Right? So if you've spent the time to understand what's happening in each of those questions, when it gets to the exam, vomit that words and drawings onto the page, and you now have full credit for that question. Okay? But that means you've got to spend the time. Right? With that, I'm going to say we're done.